All right, so we're going to talk about heat and heat technology at this point, but we're going to break this up. It's a lot of information, so we're going to break it up into three separate parts. So please make sure you view each part as appropriate relative to what we've done in class. So the first thing we really want to talk about is we want to make sure we understand the difference between like temperature and heat and thermal energy. But first, let's jump into what temperature is. So temperature, as we've talked about before, this is just the average kinetic energy of all the particles that make up an object, and it's measured using a thermometer. So as the amount of as the particles in a substance move faster and faster and faster, they get more kinetic energy, and therefore the temperature increases. That the average kinetic energy of those particles increases. So it really comes down to how much those particles are moving, because kinetic energy of the particles is really just how much those particles or how fast those particles are moving. But the faster the particles are moving, the more kinetic energy they have. So it's important to remember that temperature is an average. It's just an average measurement of the movement of the particles. And the temperature is not determined by how much of a substance we have. You can have a pot of tea and just a little tea mug that have different amounts, but they can have the same temperature as long as the kinetic energy of the particles are consistent or always about the same. So we have three different scales that we use to measure temperature. What you're probably most comfortable with and most used to is Fahrenheit, and we say it's 75 out today, 75 degrees out today. That's Fahrenheit. In Fahrenheit, the temperature at which water freezes, which we often just refer to like the freezing point, but specifically the freezing point of water, is 32 degrees Fahrenheit. And the temperature at which water boils is 212 degrees Fahrenheit. So that's kind of it's an interesting range with kind of odd numbers. So that's the Fahrenheit scale. It's probably the one you're most familiar with. Now the one we'll use a lot this year, and what most of the world uses, is Celsius. And Celsius is really built around water freezing and water boiling. So water freezes at 0 degrees Celsius and then boils at 100 degrees Celsius. Nice round numbers, really easy to look at. There is a third scale which you may be familiar with, and this is actually the SI scale, is Kelvin. Interestingly, in the scale for Kelvin, you don't say degrees Kelvin, you would just say Kelvin. And this is actually built around this number 0 Kelvin, which is what we call absolute zero. It's the lowest possible temperature, and it's at that point particles that make up objects aren't moving at all, so they have zero kinetic energy. That's what it means to be 0 Kelvin. Being built with that as your starting point, and then still wanting to maintain a 100 Kelvin shift from water freezing to water boiling, just like we had in Celsius, we end up with 273 Kelvin being where water freezes and 373 Kelvin being where water boils. So you get some really high numbers to work with, but it's all built around this 0 Kelvin, which is called absolute zero. And it is the lowest possible point on the Kelvin scale and the lowest possible temperature where substances have no kinetic energy in their particles. Now with these three scales, we can talk about like what's room temperature, like average temperature, and we have 68 degrees Fahrenheit being what's considered room temperature, 20 degrees Celsius being considered room temperature, and 293 Kelvin being considered room temperature. So those are like our room temperatures on those various scales. That would be like a comfortable temperature in a room. And that is a specific temperature. So when we say something is room temperature, that's actually what is meant scientifically, although in everyday language it's sometimes used differently. So unfortunately, not being in class, I don't have this to show you, but this is called a bimetallic strip. And it's really kind of a neat piece of metal. It's just this thin piece of metal that comes up off the handle. It's not sharp at all. It's just a piece of metal. And when you heat this up, it curves. And how much you heat it causes it to curve a certain amount, but it always curves in the same direction. And it curves at a consistent rate. It's called a bimetallic strip because one side being brass and the other side is steel. And so what's really interesting is, and some things you might be familiar with, is that when you heat things up, the particles begin to move more. We realize this, we know this is more kinetic energy, higher temperature. all this happens with the particles. But what goes along with that, if the particles are moving more quickly, they also expand a little bit. They take up physically more space. And in this case, steel expands at a slower rate than brass does, and so it causes the brass on the outside to expand more than the inside. So this started off as a straight strip. You can imagine like looking at the blade of a knife, it would be perfectly straight, but when you heat it up, it curls like this because the brass expands at a more rapid rate than the steel does, and this is due to a concept called thermal expansion, which is really just the increase in volume of a substance due to an increased temperature. And as the temperature increases, the molecules increase in their speed and movement, and therefore take up more space or volume. So that's called thermal expansion. Most substances contract as they cool and expand as they heat. There are some exceptions to this, but generally across the board, that's what happens, with only very, very few exceptions. And this is because a decrease in temperature means a decrease in kinetic energy, and therefore a decrease in the amount of space that the particles need. Now, when we talk about heat, what we're really talking about is the transfer of energy from one location to another. So instead of talking about how much energy the particles have on average, we're talking about energy being transferred from one location to another location. And it happens to always transfer from things that are warm to things that are cool. It always transfers in that direction. There's no such thing as like cold energy. You don't let cold water into the warm water. What you end up doing is you transfer energy from warm water or warm substance to a colder substance. It always works in that direction, naturally anyway. So when we talk about temperature, sorry, I went to the wrong screen here. When we talk about temperature versus heat, we're really talking about temperature measures on average how much kinetic energy the particles have, where heat is a transfer of that energy from one object to another. And it's always based upon temperature. So the transfer of thermal energy is based upon temperature, which is something to keep in mind because we'll talk about the difference between temperature and thermal energy at this point as well. So when we talk about temperature versus thermal energy, if temperature is the average kinetic energy of the particles, how much of a substance you have is not really relevant. It's just how much the particles are moving. But thermal energy, on the other hand, is the total kinetic energy of the particles of a substance. So how many particles you have does matter. You have to like add up the energy for every particle, and then that would give you the thermal energy, where the average, or just like the mean kinetic energy, would be your temperature. So if the temperature was the same between a small amount of a substance and a large amount of substance, the large amount of substance would have a greater amount of thermal energy because each particle has the same average energy, but there's more particles in total. So if we have the same temperature, this bigger amount of the substance would have more thermal energy. So thermal energy is really the total amount of energy, all the particles that make up a substance, and we measure it in the unit joules. All right. So thermal energy does depend. Does it depend partly upon temperature of a substance? Well, yeah, it kind of does, because as the temperature of a substance increases, if everything else stays the same, the thermal energy increases. If everything else stays the same but the temperature decreases, then the thermal energy would decrease. So, yeah, it is a relevant factor. Temperature of a substance is relevant in this case. What about if we had like a hot cup of soup versus a pot of the same soup? Would they have the same thermal energy? Well, no, they wouldn't, because there's more particles making up the soup in the pot than there is in the cup. So you have more thermal energy in the pot than you do in the cup. What about a cup of water at 283 Kelvin versus a pot of water at 283 Kelvin? Do they have the same amount of thermal energy? Well, same situation. The pot of water has more particles, and so it would have more thermal energy if everything else stayed the same. So it would be, in this case, we'd have like we would have the different amount of thermal energy even though the temperature is the same. All right, so that's going to be our end of part 1 for our video. So please come back, check out part 2 and part 3 as well. Thank you.